All right, so let's review our vocabulary for relations and functions. So the Cartesian coordinate plane is defined as being composed of x and y axis. Why? Why do I say the x and y axis specifically? True, because vertical, horizontal, but the Cartesian plane, why would I specifically say x and y? There's another reason. Think of geometry.
Oh, you have the z-axis.
There's also a z-axis. That's a 3D, right? 3D space. That's when we call it space instead of a coordinate plane. A plane is only in the x and y, two-dimensional. Space involves also a z-coordinate, right? Okay. No negativity, right? It's going to be an effort. You got to make an effort. Okay, so quadrants. Quadrants can be explained with just a picture, correct? 1, 2, 3, 4, going in a counterclockwise fashion. A relation is a set of ordered pairs. Domain is a set of the x-coordinates. What were you going to say? True, because 0 would 0, 0 be the origin, right? Range would be my y-coordinates. A mapping would be exactly what we were talking about kind of when you first came into class, our discussion. A mapping. That's what we were talking about before. A function can be described as each domain is paired with one range. So just like my candy bar example, you can only have one value for a candy bar. Two different candy bars could have the same value, but you can only have one value for a candy bar. Right? It only has one range. A one-to-one function, on the other hand, is each range is paired with only one domain. So that would be something more like each one has its own. That's a one-to-one function. Continuous means a line or smooth curve For a relation to be continuous, it must either be a line or a smooth curve and have infinite elements. We describe infinite elements with arrows, correct? Like that, or that would be a smooth curve, a quadratic, right? With infinite elements. And discrete, on the other hand, is a set of individual points. And this can be kind of confusing to students. This is a set of points. Somebody asked me in the last class, but when we graph, we have a set of points and we make a line. Well, we're saying that each one of those points is a solution of that line, correct? But when I just have points like this and they're not connected by a line, that could be a best fit line, but it's not a line because it doesn't include all the space in between. So this is a discrete set right here. Okay, discrete, individual. Continuous is a straight line or a curved line with infinite elements. All right, questions on that? Any of those? Okay, let's use them. All right, with your whiteboards, grab your whiteboard. And tell me if this is, with a yes or no, or a y or an n, is this a function? Okay, so we decided that this is a function because a candy bar can be two different values. This is not, no wait, it is two different values, so excuse me, this cannot be a function. So no, a candy bar cannot be $21 and $25 at the same time. This one is a function because a $5 bar and it could be $105, and a $15 bar could be $105. They both can be, correct? This one was a yes. For each domain value, there's only one range, right? And this one did not pass the vertical line test. Moving on, pencils down. Okay, so let me pause one quick second. Okay, so this set of ordered pairs, 2, 8, is going to be 5, 6, 7, 8. Sometimes that happens to a graph. 3, 5 is 1, 2, 3, 1, 2, 3, 4, 5. 5, 5 would be here. 1, negative 2 would be here. The first thing I'm going to ask myself is this a function? Well, does it pass the vertical line test? Here's my vertical line, and as I move it across, it's never coinciding with anything other than just one set of ordered pairs. So yes, it passes. This is a function. Then I'm going to ask myself, what are my domain values? The set of numbers with 2, 3, 5, and 1, just like that in set notation, because if I were to write something like this, that would be a point, correct? Then I'm going to say, what are my range values? My range values are 8, 5, I don't need to write 5 twice, and negative 2. They're all right here. And finally, I'm going to ask myself, is this continuous or discrete? Continuous would be a line or a smooth curve with infinite elements. That this does not have a smooth curve or a straight line, so this would be a discrete relation. Look at my steps here. Graph, vertical line test, domain range, discrete or continuous. I want you on your whiteboard to either, you can go ahead and plot the points if you'd like, or if you can just see it and tell me whether or not this is a function. Okay. Good job, good job. So I'm going to plot it. 2, 3, 3, 4, 4, 2, and 2, negative 2. This is not a function because it does not pass the vertical line test. You can try those over there too. So not a function. B, I need my domain values. Please show me my domain values. I just want the domain values. Okay, again, very good. We have a 2, a 3, and a 4. And your range values, please? All right, fantastic. So everybody got 3, 4, 2, and negative 2. And finally, C, is it continuous or discrete? Okay, so yes, this is a discrete, if I could spell it correctly, a discrete relation. Pencils down again. Okay, let's talk about parent curves for a second. Okay, just relax. Take a moment. Y equals X is the most basic parent curve, correct? That is a straight line, right through the origin, even though that one's not. Negative X, Y equals negative X in the negative direction, negative slope, correct? Y equals X plus 1 is a regular line, straight, with not a steeper slope or a less steep slope, but shifted up 1, right? Y equals, let's do 4. Y equals 4X. Steeper, because 4 times something is going to make it shoot up in a faster rate, correct? So a steeper line. Y equals 1/8 of X. When you take a fraction of something, as fractions go higher and higher and higher, isn't it getting closer and closer to 0 on a number line? Like if this is 1, this is 0, and this is 1, as the fractions get larger, here's a half, a fourth, an eighth, right? Isn't it getting closer and closer to 0? So if you put that in front of that X, your line is also going to get closer and closer to 0, 0 being right here, right? So what about Y equals 1/8 of X plus 2? Would be this line only shifted up 2. Okay, those are parent graphs and behavior of graphs. Then we had something like this, Y equals X squared. When you square it, it becomes quadratic, right? So now you have 2 values for X, in the positive direction and the negative direction, right? Y equals X squared plus 1. Shift it up 1. Y equals negative X squared. Y equals, let's write it, Y equals negative X squared plus 3. Shift it down, or pointing down, but shift it up 3. So these you need to become really familiar with. I think it's more important to understand the behavior of the graph than to do that table right there. Because you can do a table and mess up somewhere. But if you understand the behavior of a graph, you should know, wait, I'm way off, because my parent graph looks like this, and it should be shifting up, and it should be in the positive direction. So it really is very helpful if you understand the behavior of graphs. And this isn't the only time I'm going to talk about it. I'll talk about it all year long. Okay, I just want to show you a preview of it. This one looks different. How does this one look different? Y is squared instead of X being squared. So when we talk about X being squared, X has mirrored, or has symmetry, right? On each side, in the positive X and in the negative X. Well, the parent graph of this would be, which looks like that. Which makes sense because Y can either be, if I put in a negative 1, I'm going to get 1. If I put in a positive 1, I'm going to get 1. So your symmetry now is with respect to the y-axis instead of the x-axis. So that being said, just guess, don't tell me, but just guess what you think x equals y squared minus 1 is going to look like. And I'm going to use this table of values, and we're going to make sure we know what it looks like. Okay, so I'm going to put in the easiest point to substitute in. We normally would plug in or substitute in 0 for x. But in this case, it's kind of in the reverse. We need to put in a value for y to find x. So I'm going to put in 0, and when I put in 0, I get negative 1. So 0, if I use this as that's my ordered pair, right? Negative 1, 0. So that's where I'm going to start right there. Next easiest number to put in would be 1. So if I substitute 1 in for y, I get what? 1 squared minus 1 is 0. Right? So our ordered pair is 0, 0, 1. So if I know I'm going to go up 1, I'm guessing I'm also going to go down 1 as well. Let's try negative 1. If I substitute in negative 1, I also get 0. So I was right. 0, negative 1. I can kind of see the shape starting. Let's go with 2. See what happens. X equals 2 squared. Let me see what time it is here. Okay, we're pretty good. Minus 1. 2 squared minus 1 is 3. So 3, 2. So at this point, I really don't need this last point, because I know if there's symmetry, then if there's a point here, then there must also be a point here. So, A, is this a function? No. It does not pass my vertical line test. B, what are my domain values? This is the toughest part, I think, of these graphs. So when you think about it, your x values, is there ever going to be an ordered pair in this direction over here? Ever? No. The ordered pairs start here, then here, then here, then here, then here, then here, and infinitely in this direction, because we have arrows right here. So my domain begins x such that x is greater than or equal to negative 1. Starts right there, and it goes in that direction forever. Okay? The reason why on here you have domain values that are just singular values is because these are points, right? So your domain values are only dealing with these discrete points. But if it's a continuous function, or this isn't a continuous relation, I should say, then I've got infinite points in here. I just haven't graphed them. But they're all there, right? They're all there. If I were to put in negative 1/2, I would get a value. If I were to put in 2.5, I would get a value, right? If I put in negative 2, am I going to get a value? No. Negative 2 is not in the domain. Negative 3, if I put in negative 3, am I going to get a value? No. Right? If I plug in negative 3 for x, y is not going to be anything. It doesn't exist because it's not part of the graph. All right. C. No, not C. What do we still need? We still need a range. My range values. And by the way, this is the hardest one. Okay? The hardest example. Range. Range are my y values. Okay? So my y values, no matter what, if I plug in 0, I would get a y value. I'm sorry, I would get an x value. It's this right here. If I plug in 1, I got an x value. The x value was 0. If I plug in a negative 1, I got 0. If I plug in 2, I get something. If I plug in negative 2, I'm going to get something. Right? It's going to keep going this way and this way, and it keeps going this way, right? And out further and out further. So, in both directions of y. Correct? Right? If I plug in that, is that eventually going to hit the graph? Yes. If I plug in negative 2, is it eventually going to hit the graph? Yes. 3, is it eventually going to hit the graph? Yes. If I plug in negative 4, yes, it'll plug in over here. If I plug in negative 5, yes, it'll be way out here. Same in the positive direction. Up 1, there. Up 2, there. Up 3, out here. Up 4, way over here. Up 5, way over here. Am I always going to have a y value? Very difficult, abstract. All real numbers for y. All right, let's do another one. So I don't have time for whiteboards, but I'm going to go ahead and do this one for you. So I've got y equals negative 2x plus 1. I tell myself, I know that I have a parent graph, and I'm going to use it. Negative 2x is a negative line. Plus 1 means it's shifted up 1. And because it's 2 times x, I know, you guys, can you not put the boards away right now because it's distracting to me? Just leave them there. Okay, even though I know you're just trying to clean up. So this graph should look something like that, just from what I know about it, right? From behavior of graphs. So I'm going to go ahead and do the easiest one. I know from y equals mx plus b, shouldn't be using blue for that, that this is my y-intercept, positive 1. Makes sense, right? Shift it up 1. Okay, so I know if I plug in or substitute in 0 for x, I'm going to get 1. Next easiest number to do would be 1. Y equals negative 2 times 1 plus 1 equals negative 2 times 1 is negative 2 plus 1 is negative 1. That's my next point. 1, negative 1. Most of you should see a pattern right now. I've got a slope. Rise over run, right? Up 2 over 1. Where do you think the next one's going to be? Up 2 over 1. Let's see. If I plug in negative 1, I would get negative 2 times negative 1 is positive 2, plus 1 is 3. Negative 1, 3. I'm right. I'm guessing I could do it the same way in the other direction. If I can go up 2 over 1, I can go down 2 over 1. And I could test that, but I'm pretty positive I'm correct. Next, I need to ask myself, is it a function? Does it pass a vertical line test? And it does. Make it a different color. No matter where I take this vertical line, it is only going to hit my vertical line once. So yes, this is a function. Domain would be, if I substitute in 1 for x, am I going to get a y value? Yep, it's going to be down here. Go in this direction? Yep, it's there. This direction? Yep. Always, right? Go in the positive direction? Let's go the negative direction. Am I always going to get a value? All real numbers. Range. Let's go up. If I go up, is it going to hit the graph? Yes. If I go up again, am I eventually going to hit a graph? Up again? Yes. Up again? Yes. It's always going to hit, right? What about the negative direction? If I go down? Yes. Down? Yes. Down? Yes. Always, right? Also, all real numbers. Okay? And finally, is it continuous or discrete? It's a straight line, right, with infinite elements in either direction. This is a continuous relation. And I did not spell that right because I'm going too quick. Last thing I want to show you, which I don't even think I need to explain, is this. Find h of negative 2 if h of x equals x cubed plus 1. All you have to do is substitute in negative 2. So everywhere you see an x, you put negative 2, and you just simplify. So there's your notes. You don't have to write them out. If you want to, you can. I've also got them online. Thank you so much for waiting until I finished. Which one? Wait. Yes, I am recording, but I want to hear this question. On this one. Yes. Because, hold, guys, This is an excellent question. Can I get you guys to stop? He wants to know how come I didn't write 0.
-1. X from X.
Okay, notice that I said X such that X is greater than or equal to -1. I have -1, I have 0, I have 3. If I plugged in 4, 5, so it says -1 and every single number that's above that. Like this? Does not need to be written like, it needs to be written like this. What you're not including, if you don't put this sign right here, you haven't included a half, a quarter, a third, 2/3, 7/8. All of those are included in here. The difference between it is, like on this one, the reason you can just put individual values is because these are points. But a graph, this line right here, guys have a great day, this line right here includes every single little point that's in here. You don't want to write every single little point because there's infinite many of them.
You have our blue sheets of paper.
You know what I mean? Is that a little bit better? I'll try and address it more on Monday, okay?
The homework.